I'm going to assume that of all the things that we've talked about, that you may have forgotten some things. And you may not recall every little nuance of every discussion that we've had. I think that's kind of a predictable situation. My students, for example, have trouble remembering things that we've talked about. And how do you recall those? That's the technique that I want to emphasize here. That it's okay if you forget some information. You're not supposed to go and memorize a whole bunch of stuff in order to understand trigonometry. The word understand is the operative word here for trigonometry. You base your understanding on some critical information, and that information has to do with the trig ratios, number one. You do need to remember those, and at this point, with all of the practice that we've had with them, you probably already know them. And I think you can reduce the amount that you remember just by remembering the ratios of sine, cosine, and tangent, and just remember that the other three are reciprocals of those first three. Right? And if you know those reciprocal relationships, then you're fine. All right, the other idea is that we talked about some sort of familiar or reoccurring angles, 30 degrees, 60 degrees, 45 degrees, and we talked about sine, cosine, tangent of those three angles. And we said that we ought to commit those to memory. Well, maybe and maybe not. Well, even if they're not in memory, though, we can recall them by using the sketches of them. And that's what I want to show you right now. How do we analyze a situation like this? Now, let's suppose that we can't use our calculator. If we can use our calculator, we can perform the operation in about 5 seconds. But let's suppose that we can't use the calculator. We want to make the calculation by hand, and we should be able to do that, even though we have calculators at our disposal. It's important to be able to analyze through this because we have a better concept of the whole idea if we're able to do that. Okay, cosine of 4 pi over 3. Well, now I'm going to think through it as you might think through it, and I'm forgetting a lot of information. Okay, so I might think, well, I know that when pi is involved, I'm talking about radian measure, so I might think of this as cosine 4/3 pi, and I want to kind of separate my thinking like that because I know that in the coordinate plane I have some points of pi and 2 pi, and those are really important points on the overall coordinate plane when I turn angles of those sizes. Okay, so this then is now 4/3. 3 goes into 4 one time with 1 left over, so this is 1 1/3 pi. Oh, good. Now I can think about the coordinate plane, and I know that this is pi, this is 0, and it's also 2 pi if I go all the way around, okay, in terms of radian measure. This is pi over 2. Okay, good. Now, 1 1/3 pi. 1 pi would be an angle to this point. 1/3 beyond that, 1 1/3 pi, you see, would take us around to, oh, maybe right in here. Okay, good. Now we have an angle in the third quadrant. Okay. And I have a reference angle right in here. And I can think about a reference triangle if I want to. And now, this reference angle, how big is that angle? Well, let's see. This is 1 pi. The whole angle is 1 1/3 pi. So I take 1 1/3 and subtract 1 pi, and I'm left with 1/3 pi. 1/3 pi, okay. So our reference angle here is 1/3 pi, or simply pi over 3. Wait a second, I recognize that as one of the familiar angles I was supposed to remember the value of, but I don't remember the value of it. What can I do? Well, you know, I kind of have a feeling for the angles in degree measure a little bit better than the angles in radian measure because maybe we've been using those a little more frequently. So what I can do about that is this. I can think, well, let's see, I know that pi corresponds with 180 degrees. And even if I don't remember the formula for changing from one kind of angle to another, I can understand the problem this way. Pi over 3 is what I'm trying to figure out. Now, from pi to pi over 3, I'm dividing by 3. If I divide by 3 over here, I find this to be 60 degrees. Oh, this is the 60-degree angle that corresponds with pi over 3. Now, I could put that back into my diagram, but I know that cosine of the angle pi over 3 is the same as the cosine of 60 degrees. All right, now, I've got a little situation going on with both the calculation for the cosine of 60 degrees as a reference angle of the triangle and also the sine associated with the situation. The sine. Well, let's analyze what the sine pattern is. I forgot what it was. Okay, I know that cosine is adjacent over hypotenuse. So I've got the adjacent side is an x value and the hypotenuse is always positive when I'm talking about turning angles and reference triangles and so forth in the coordinate plane. So the x, though, is negative. So cosine is negative here. Oh, now I remember. It's the x idea, and so, whoops, it's the cosine of angles in the third quadrant are negative, and also negative in the second quadrant, but positive in first and fourth. Okay, I remember that now. All right, so I know this much, that the cosine of this angle is going to be negative, and now all I have to do is figure out the cosine of 60 degrees. Well, I forgot what it was. Okay, so if I forget what it was, then I'll go to my little reference triangle, and my reference triangle might look like this. So I've got a 60-degree angle here, and I remember there was also this 30-degree angle up here. And now, gee, I forget the values for the sides. I think it was 1, 2, and the square root of something, but I don't know exactly where they belong. Well, let's go back to the idea of our original discussion with this. Our original discussion started out with an equilateral triangle, a triangle in which all the angles are 60 degrees and all the sides are the same length. Okay, and then we bisected this rascal. We said, okay, if this was a 60-degree angle, then after we bisect, that's 30. Oh, here's our 60 right here. Here's our right angle. Now we just make the sides convenient. Now it's convenient to make this side 1, and therefore this is 1, and the whole thing is 2, and that's 2. So we have, oh, here we go. Now take all of this out in your imagination. We have 1, 2, and what's this? Well, if we need to, we can go to the Pythagorean relationship and figure it out. It turns out to be the square root of 3. So we have the 1, 2, square root of 3 triangle that we refer to in making our calculation. And we're thinking about, let's see, the cosine of 60 degrees, that's adjacent over hypotenuse, so it's 1/2. And therefore, the cosine of 4 pi over 3 is negative 1/2. Okay, so that's the way you kind of think through it. Let's go through it one more time. Let's use another one. Now, this one may seem even more imposing, the cosecant of 11 pi over 4. Well, we start the same way that we did with the other problem. You think cosecant, and now separate a distinct coefficient from pi. We have 11/4 pi. All right, now, how many times does 4 go into 11? So we think cosecant of 4 into 11 goes 2 with 3 left over. So this is 2 and 3/4 pi. Now, what about on the coordinate plane? Well, let's see. We've got on the coordinate plane, I know that this is pi, there's 2 pi. It's either 0 or 2 pi. So I'm talking 2 and 3/4 pi. So 2 pi would be an angle all the way around to here, you see. And then 2 and another 3/4. 3/4. That's 3/4 of pi. Pi would put us back over here. 3/4 pi means 3/4 of that amount. Oh, that's about right in here. You see, so here's 2 and 3/4 pi. So our angle then falls into the second quadrant. All right, now, all right, what are we going to do about this? Well, we're going to create a reference triangle and a reference angle. Now, what about the reference angle? We've got, we can throw out the 2 pi part of it and think about it like this. What's 3/4 pi? And the reference angle for that? Well, we take pi and subtract 3/4 pi. Oh, that leaves us with 1/4 pi, 1/4 pi, or pi over 4 for our reference angle. Oh, this is another one that I was supposed to remember. I forgot the relationship to angle measure in degrees, and so I might go to the side and do the same thing that we did on the previous problem. I might think, well, 180 degrees, whoops, excuse me, pi corresponds with 180 degrees. And pi over 4 then corresponds with 180 over 4. Let's see, that turns out to be 45 degrees. Oh, that was one of my handy-dandy reference angles and a little triangle that I can construct here. And that triangle looked something like this. Remember, if this is 45 degrees, then this other angle is 45 degrees. If the angles are the same, the sides opposite them are the same, so we made it easier on ourselves, 1, 1, and this turned out to be the square root of 2. Okay, oh happy day. We have now for the, let's see, we're talking cosecant. Uh-oh, I forgot now. I've got my reference triangle. I've got all of that. I need to know something about the sine here, and I need to think about the fraction that is cosecant. Okay, let's talk about the fraction first of all. Cosecant, maybe I forgot that the ratio that corresponding with cosecant. But I do know this, that cosecant, along with secant and along with cotangent, are all reciprocals of the primary three trig relationships. And you know, I forgot which one it's the reciprocal of. So what I could do is this. I could think, well, I know that they ran in a pattern, that we had sine, cosine, tangent, and then cotangent, and then secant, and then cosecant. Oh, okay, and the reciprocal situation went like this. Okay, I remember that. Now, okay, so cosecant then is the reciprocal of sine. All right, good. Now, sine I know to be opposite over hypotenuse, so this is hypotenuse over opposite. So I'm talking about, let's see, hypotenuse over opposite. Now, if this is my reference angle, hypotenuse over opposite would be the square root of 2 over 1. So we're talking about the square root of 2 here. So the square root of 2. Now, I'm not going to put a sign here just yet. I want to, I may have jumped the gun a little bit in finding the value of the square root of 2, because I need to identify the sign in the second quadrant. But in the second quadrant, you know, if I'm talking about, let's see, adjacent over opposite, you see it's always positive over, oh, this y value is positive in the second quadrant, so cosecant is positive in the second quadrant. So just for emphasis, I'll put a plus here. All right, so anyway, that's the way you kind of think your way through this, these matters if you have forgotten some of the information. Let's go through another problem. This one says that if sine theta is 1/3 and theta is in quadrant 2, find cosine theta and tangent theta using identities. Now, we used identities in a similar way in a previous problem. But with that problem, we were confined to the first quadrant, so all the signs were positive. Now we're in quadrant 2, and we have that to consider as an extra bit of information in this problem. All right, so let's see. The sine of theta is 1/3. Theta is in quadrant 2. Now, if we want to cosine theta, and we want to use an identity, then we have to identify an identity involving cosine theta and sine theta. Well, that's the first Pythagorean identity. That's sine squared theta plus cosine squared theta is equal to 1. Fill in for sine theta is 1/2. So we have 1/2 squared. Now, this is 1/9. So I'm subtracting 1/9 on both sides. And over here, 1 minus 1/9 turns out to be 8/9. But if cosine squared theta is 8/9, then cosine theta is plus or minus the square root of 8/9. Then now, in previous problems like this, we've just thrown this out and said we want the positive value. Sure we do, as long as we're in the first quadrant. But we're not in the first quadrant anymore. Which one of these do we want? That's the important question right now, along with taking care of this radical part. Well, let's see, cosine in the second quadrant. Now remember, cosine, let's see, cosine was adjacent over, okay, that's x. Okay, so it corresponds with how x rolls in the various quadrants. X in the second quadrant is negative. And so we're talking about the negative value here for this choice. And then the square root of 8. Well, 8 has a square in it. 8 is 4 times 2. The square root of the 4 is 2. 2 appears outside of the radical. The other 2 appears under the radical sign. So this is 2 root 2 in the numerator, and the square root of 9 is 3 for the denominator. So here's cosine theta. Now the analysis for tangent theta is easier. We have a handy identity. It's tangent theta is sine theta over cosine theta, and we have those values already calculated in the problem. Sine theta from up here is 1/3. Cosine theta we just calculated as negative 2 root 2 over 3. And now it's a little arithmetic kind of problem here. We know that our value here is going to be negative, so we could just bring down negative at this point if we want to. But here's what I did. I said that this complex fraction becomes 1/3 divided by this, but it means 1/3 times, boom, it's reciprocal. And now the 3's go out, and we have negative 1 over 2 root 2. Rationalizing, we find this to be negative root 2 over 4. In studying trigonometry using the idea of radian measure, we get high mileage out of considering the unit circle. Now, the unit circle is a circle whose radius is 1, so here's a unit circle. Now, with radian measure, we know that theta is equal to arc length over radius. That is, if we're talking about an angle theta, a central angle of theta, then that central angle is equal to arc length over radius. But gee, if we're talking about a unit circle, then the radius is 1, and so theta corresponds with arc length. Now, so this opening of theta can be considered to be the same value as we have for the length of this arc. And I'm going to call the length of that arc t, just for the time being. All right, now consider the idea that we can take a real number line, and let's say I have a real number line in my hand right here. And let's say that, from our previous experience, the positive values lie to the right and the negative values to the left. Now look at what I'm going to do. I'm just going to take that number line and I'm going to twist it like this. And I'm going to put 0 on the number line right here on that unit circle. And now I'm going to take these positive real numbers and I'm going to wrap them around this unit circle in this direction. And I'm just going to keep on wrapping. I have an infinitely long line here with real numbers, and I'm just wrapping that line around this circle. All right, and in the negative direction as well. I'm going to take these negative real numbers, and I'm just going to wrap them around this unit circle. Just wrap, 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 wrap. Okay. Now I've got a situation where I have a length of an arc. And of course it corresponds with an angle here, but let's forget about the angle for the moment. Let's just think about arc length. So we have an arc length, a real number, you see, and that real number is associated then with a point, because once we consider the real number t and we travel along the circle that length, you see, then we arrive at a point on the circle, and that point has coordinates, and the coordinates of that point are x, y. Now, let's associate this idea of arc length and the coordinates of that point on the unit circle with trig relationships or trig functions. Now, there are 6 trig functions: sine, cosine, tangent, cotangent, secant, cosecant. And let's define them this way. Now, sine is abbreviated as sin, cosine is cos, tangent is tan, and so on. All right, that the tangent of that real number t is simply the second component in the coordinates of that point where we land on the unit circle. So the sine of t is y. The cosine of t is x. The tangent of t is y over x. And cotangent t is x over y, secant of t is 1 over x, cosecant of t is 1 over y. So all of these just involve the coordinates of that point that we talked about. And also we notice that we have a reciprocal relationship between tangent and cotangent. We have a reciprocal relationship between cosine and secant. We have a reciprocal relationship between sine and cosecant. Okay, and that's kind of a handy idea as well. Okay, so now we can relate all of this back to the notion of angle. It would be okay, but we want to emphasize the idea of a real number. You see, of taking these functions of real numbers and associate them with the coordinates of points that lie on the unit circle. A really interesting twist in this study of trigonometry. All right, consider this. All right, we have a unit circle here, and I want to consider the sine of a real number t. All right, now let us just think about the value of y as we consider real numbers, as we go around here. Now, we could consider angles, you see, and it would be a very similar consideration, but just consider the notion of real numbers. That number line is just wrapped around this rascal, time and again, just an infinite number of times. Now, think about the distance t, you see, and the value of y. What's happening to y? Well, now, think about those distances. First of all, we have a unit circle here, and we know that the distance all the way around that circle is its circumference, and the circumference is pi times diameter, but that's also 2 pi r. And if the radius is 1, then the distance is 2 pi. So all the way around to this point would be 2 pi, as we may already expect. And the distance then from here to here is simply pi. Okay, so as we go a distance of pi, you see, along that unit circle, the top of that unit circle, notice what's happening to the y component. It's just a vertical distance. You see, it's going from 0 here all the way up to 1 and then back to 0. You see, and then down here from pi to 2 pi, it's going from 0 to -1, you see, vertical distance on the coordinate plane, and then back to 0. All right. Now, once we get to 2 pi, what happens? You see, we're thinking about the sign of a real number. Now, the real number is taking on values from 0 to 2 pi. And let's put a real number on that we can maybe more effectively deal with. Pi is approximately 3.14. 2 pi would be about 6.28. So once we get to about 6.28, you see, then what happens? Once we get beyond 6.28, then we're wrapping around that circle again. You see, and the values that the sign of the real number takes on begin to repeat from the original. You see, the sign of a very small real number, you see, had a certain value, and its value corresponded with y, and so on. But when we get beyond 6.28, we get to that same value again. You see, and the values for y, again, start to become 0, and then 1 to 1, and back to 0, and -1, back to 0, and so on. Now, this idea that we are repeating the values for the sign of real numbers, as the real numbers increase in value, this y value is changing in a almost melodic, wave-like form. That is, the y value is going from 0 to 1 to 0 to -1 to 0 to 1 to 0 to -1 to 0, and so on. Now, this is called periodic behavior. And this kind of behavior occurs with all of the trig functions. That we have this notion of it going through a period, through a cycle, if you will, and then the cycle simply repeats. Okay. Now consider the idea that I can take a particular real number, like, let's say, pi over 3. Now, in identifying pi over 3, I'm saying that's this arc length. Okay, and again, I can associate it back to an angle if I want to. And I can associate that angle with an angle measured in degrees if I want to. That's fine. But right now, we're thinking about an arc length here of pi over 3. And that arc length is associated with a point on the unit circle whose coordinates are, let's say 1/2 and the square root of 3 over 2. Let's say those are the coordinates of that point. Now, if those are the coordinates of a point associated with an arc length of pi over 3, then we can generate our trig functions just with this information. And here's how it works. T, a real number, you see, of pi over 3, corresponds with a point on the unit circle whose coordinates are, given here, find sine of pi over 3, the sign of that real number. Well, the sign of a real number is simply the y associated with it, and the y is the second component in the coordinates of a point. So this is simply the square root of 3 over 2. And in a similar way, all the rest of the trig functions fall. We have the cosine of that real number is x. The x component is 1/2. The tangent of that real number is y over x, so that's this fraction over that one. You see, and now cleaning this up a little bit, the 2's go out and we have the square root of 3. Now, the other trig functions turn out to be the reciprocals of the first 3, so they're pretty easy to generate. These two are reciprocals of one another, and so the cotangent of pi over 3 is 1 over the square root of 3, which we can rationalize if we want to. I'm not going to right here, but we could here. Then the secant of pi over 3 is the reciprocal of cosine, and so the reciprocal of 1/2 is 2. And then cosecant and sine are reciprocals of one another, and the reciprocal of the square root of 3 over 2 would be 2 over the square root of 3. And once again, we could go through the rationalization process if we wanted to. Let's go through another one like this. Suppose the real number t is 3 pi over 4. And suppose that real number, now the real number is along the unit circle, you see, and it has coordinates associated with that final point along the unit circle. And the coordinates of that point, let's say, are these. And we want to find our various trig functions. Well, once again, it's just a matter of looking at the coordinates of the point. So the sine of that real number is equal to the y component, and that y component is the square root of 2 over 2. All right, and then the cosine of that number is the x component, and it's the negative square root of 2 over 2. And the tangent of that one is a y over x, and it turns out to be, let's see, this fraction over that fraction, and that turns out to be -1. Now notice the same fraction here, difference only in sign from numerator and denominator, so we get -1. Now we go through this reciprocal process. The reciprocal of -1 is -1. The reciprocal of this is -2 over root 2. Now when you rationalize this, it turns out to reduce to negative the square root of 2. And I went through the process right here. You remember the way to do that is to multiply both numerator and denominator by the square root of 2. In the denominator, you get the square root of 4, which is 2, and that 2 cancels with this 2, and you're left with the factor of the square root of 2 in the numerator. Okay, that's how that goes. All right, the cosecant is the reciprocal of sine, and once again, you just flip that fraction over, rationalize, and you get the square root of 2. All right, so that's the idea. Now, there are some particular values that t can take on that we can analyze by identifying the coordinates of a point associated with the real number. And it's not difficult to do, like this. Suppose t is equal to pi. Now, just think about the unit circle and think about the distance here along our unit circle over to, pi is right here. Remember, it's 2 pi for all the way around, but it's pi up to that point. Now, what are the coordinates of that point? Well, that's really what we're after here. So we've come around to pi. That distance is pi, you see, and the coordinates of the point would be, well, let's see, it's a unit circle, so we have -1 for the x component, and y is 0. So it's -1, 0. And now we can generate our trig functions. The sine of pi then would be, let's see, it's the y component, and that is 0. The cosine of pi is the x component, and that's -1. The tangent of pi is, well, let's see, it's y over x. So that would be 0 over -1. Oh, that's 0. And now the cotangent is the reciprocal of 0. Uh-oh, be careful here. The reciprocal of 0. 0 can be thought of as 0 over 1. So its reciprocal is 1 over 0, and 0 in a denominator causes an undefined fraction to occur. So here we have an undefined value. And now secant is the reciprocal of cosine, so the reciprocal of -1 is -1. And for cosecant, it's the reciprocal of 0, and once again we get an undefined value. I've identified the coordinates of some key points on the unit circle. And we understand from our previous discussion that for every real number, we have a distance along the unit circle. And if that distance is, let's say t, then we have some distance t, and at the end of that distance, we have a point, and that point is associated with coordinates x and y. Okay, now let's think about the notion of domain and range for our trig functions. And for example, if we're talking about the sine of real number t being equal to y, then the domain would be the acceptable replacements for t. Well, we're thinking about t as being any real number. You see, we can take the sine of any real number, so the domain of this function is all real numbers. What about range? Well, range refers to the values that y takes on. You see, sine of t would be some values. Now, for what values do we get when we take the sine of real numbers? Well, we can examine that pretty easily over here. We already have a pretty good idea of what that's going to be. It's the notion that the sine is associated with just a y value, and that y value changes from 0 to 1 here in the first quadrant, and then in the second quadrant we go from 1 to 0, and then in the third quadrant 0 to -1, and then in the fourth quadrant -1 back to 0. So our y values are changing from, well, the smallest y value we can get is -1, and the largest one is 1. So the range would be -1 is less than or equal to these y values, and the y values are less than or equal to 1. And in a similar way, we could examine domain and range for the other trig functions. Well, the periodic nature of our trigonometric functions leads us to this algebraic idea. Now, we know that the periodic nature is that we can take the sine, for example, of numbers that wrap around our unit circle, and that once we get back to 2 pi, once we go all the way around this distance of 2 pi, then the values for the sine of those real numbers will begin to repeat. Okay, now with that in mind, we can say this then, that the sine of a real number t is equal to the sine of that real number plus 2 pi, or even minus 2 pi. You see, for whatever value t is, if we add 2 pi, we're just going all the way around the circle again, and we end up at the same spot. If we subtract 2 pi, we end up at the same spot. But we could add or subtract another 2 pi, and another, and another, and another, and end up at the same spot. So indeed, we could say that the sine of t is equal to the sine of t plus n times 2 pi, where n is an integer. Now that integer, can be either positive or negative, so we can either be adding or subtracting units of 2 pi here. Now that kind of helps us to evaluate in situations like this. We have the sine here of 5 pi. Well, I know that this is the sine of 5 pi plus or minus any number of 2 pi units. So I can say this is the same thing then as the sine of 5 pi. Let's take away 2 pi units. That is, let's take away 4 pi. You see, 5 pi minus 4 pi, oh, that's simply 1 pi or pi. Now the sine of pi. Whoa, I know something about the sine of pi. I know that a distance of pi, you see, is a distance around to this point. And oh, the coordinates of that point are -1, 0. And I know that the sine of a real number is equal to the y component, and so this becomes simply 0. And in a similar way, sine of this value, well, let's think of it like this. It's the sine of, now I'm going to separate the notion of the coefficient with the pi, so it's -7/2 pi. That's the way I want to think about it. And 7/2, well, let's see, as a mixed number, I might be able to see things a little bit easier. So it's minus 2 and a 7 goes 3 with 1 left over. So this is -3.5 pi. Well, I can add units of 2 pi here, add or subtract if I want to. I think I want to add units of 2 pi here, maybe a couple of them. So this is the same as the sine of -3.5 pi plus 4 pi. You see, and -3.5 plus 4, oh, that's a half a pi. You see, or pi over 2. So this is really the sine then of pi over 2. Now what is that? Well, I know something about that too. That's one of those important points along the curve or along the circle. If I'm thinking about the circle like this, and this is pi, then this is pi over 2. And if it's a unit circle, then the coordinates of that point are, let's see, 0, 1. And when I'm talking about sine, I'm talking about the y component, so the sine of pi over 2 is equal to 1. Now let's think about the sine of real numbers in the positive direction and negative direction. sort of at the same time. That is, how does the sine of a real number t compare to the sine of a real number negative t? So it's kind of like we're wrapping in both directions here almost at the same time. So now we know that the sine of t is equal to y, and let's just pick a point here. I'm going to pick this point. Here's the point xy. Now, and here's t. Now, if I'm thinking about negative t is going out in this direction, and the distance here is the same as the distance there. You see, I mean, their absolute values are the same, and so we travel the same amount of arc down here that we do up there. All right, that's the idea. And the coordinates of this point, then, would be x, same x now, but it's the negative of that y. You see, now, so the sine of negative t, then, the sine of negative t would be negative y. Okay, so it appears, then, that as we wrap in opposite directions, the sine will be, then don't confuse the S-I-G-N with the S-I-N-E. You see, and it's easy to confuse in a situation like this because of the context of the discussion. But the S-I-G-N is just different for these two, it appears. You see, when these S-I-G-Ns are different, then those S-I-G-Ns are also different. I wonder if that's true over here. Now remember, we're talking about y components. So if I'm talking about a t that takes us around to the second quadrant, I'm still talking about a positive y. And a negative t of the same value would take us over to a point over here. So we would have a negative y. You see, a negative of the same y that we have up there. Okay, so it seems to be kind of universally true, and as we wrap around this way and that way in opposite directions, we get the same kinds of results. So it seems to be the case that the sine of negative t is equal to the negative of the sine of t. Now, this kind of notation, we've seen this a little bit before when we were talking about function notation in one of the earlier chapters, and we can actually put a label on the kind of function. This falls into a category of function called odd. So this is an odd function because of this kind of circumstance or this kind of situation. Now, actually, I bring it up here. The more important idea is not so much important that it's an even or odd function, although that is an important matter, but it's relative to the notion that we can make the calculation of the sine of negative real numbers by just taking its positive counterpart. Sometimes it's just easier to look at it in sort of the positive direction. Take the positive one and then just attach a minus sign to it. You see, at the end of the problem. It's just sometimes an easier way to evaluate the situation. Okay, now, what about for cosine? Now, cosine of a real number is equal to x. What about the cosine of the negative of that real number? Well, again, we would just choose a distance t and coordinates of a point as xy, and think about a distance of negative t, and the coordinates of that point would be x and negative y. Now, we're talking about the cosine of the real number is equal to the x component, and the x component is the same for both of these. So if the cosine of t is equal to x, then the cosine of negative t is also x. You see, now, that's true even if we're talking about items over here, that we're talking about a t that has an xy pair up here, an x negative y pair down here. You see, so the x component, although the x over here would be a negative value, you see it's negative something or other, and the y, well, we don't care about, but it's a negative x over here, but it's a negative x over here as well. So it's that x portion, you see, that we're thinking about. It's that part that we're after for the component involved in the calculation of cosine. So the cosine of negative t is also x. And so therefore it's the case that the cosine of negative t is equal to the cosine of t. Yeah. And again, this is important because when we're finding the cosine of negative real numbers, we can just consider it to be equal to the cosine of its positive counterpart. you see. And now in terms of even and odd, this was the situation where it falls into the category of an even function. Now what about for tangent? Well, maybe this isn't quite as easy to evaluate as sine and cosine, but let's take a shot at it. We have, let's see, the tangent of t is a y over x, and once again we have a t distance here, and it's associated with an xy pair. And in the other direction it's the negative t, and again it's an xy pair. But this time it's the same horizontal component that we had up here, but the vertical component is the negative of that y upstairs. Okay, so when we're thinking about this this fraction, this ratio, then we're talking about, let's see, the ratio of those two for the sine of t, and the ratio of these two for the sine of for the tangent of t and the tangent of negative t. And it's the negative of y over x. And I want to think about the SIGN of the entire fraction and not just numerator or denominator. So, and the situation carries forth as we go into the second and third quadrants and so forth. We have a sign difference in the fraction for the values as we wrap around in the two different directions. So, kind of like the sine, we have a situation where the tangent of negative t is equal to the negative of the tangent of t. And once again, this falls into the category of odd function. Well, let's talk about using the calculator, and this will be no surprise to you. We just have to make sure that the calculator is in radian mode. That's the most important thing. So if we're finding the sine of the real number 2, you see it corresponds to 2 radians, and so all we have to do is select radian mode and enter it into the calculator as we would expect. Sine 2, enter, and the value is approximately 0.91. Notice a value between -1 and 1, within the range of values for the sine function. Now for cotangent and for secant and cosecant, the calculator doesn't actually have a button for those 3 trig functions, but they're pretty easy to calculate because they are the reciprocals of either sine, cosine, or tangent. So here's what we have to do. We just have to realize that now the cotangent of a real number is the reciprocal of the tangent of the same real number. So on the calculator, we find the tangent of that real number. And to do that, we enter tangent, 2 pi divided by 3, close parenthesis. This parenthesis was automatically opened when you press tangent. All right, so you close the parenthesis. And now what you want to do is take the reciprocal of this. And on the graphing calculators, it's generally designated as x to the -1. That means take the reciprocal of this, press enter, and boom, we have negative 0.58 approximately as the cotangent of that real number.